me just share my screen first. Okay, so very quick recap. What we have done so far, Lie groups are groups, which are groups and manifolds. So elements in the Lie group, elements like A, B, C, have a bunch of parameters. If you have a R-dimensional manifold, you have alpha 1, alpha 2, up to alpha R for A, and so on for B and C. And the basic idea was a relationship like AB equals C translates to a relationship between the parameters. That is, gamma J's, the parameters for C, can be written down as functions of alpha and beta, the parameters for A and B respectively. Again, we have seen this before. We choose our parameters in such a way that the identity element gets a bunch of zeros as parameters. And therefore, if you put in 0 for either the first or the second argument in F, the other argument always comes out as simply A into E equals E into A equals A. And from that, we argued that if you did a Taylor expansion of Fj, the jth coordinate, jth function, in terms of alpha and beta, it must have this form. Of course, there will be higher order terms as well. But the important thing is no pure alpha terms or pure beta terms beyond these two. We then went on to define this quantity, the eta jk, which were basically the rate at which the function changed with its first argument at the value of that first argument being 0. And then we showed that associativity implies that you must have this condition. That is, the derivative, the rate at which fj changes with alpha k at all alpha, not just alpha equals 0, can be written down if you know the etas and their inverses. And we also said that we should be able to, in principle at least, integrate this equation given the etas and find out fj alpha beta with the beta j's as the initial values, and essentially playing the role of parameters as far as these equations are concerned. We also showed that the functions that we would find by solving these equations actually satisfied the associativity condition. And then we had this integrability condition, which is sort of something which you have learned about partial derivatives from our very beginning. And there, it translates to, after a sort of lengthy manipulation, it translated to this bunch of conditions. That is, this particular combination of zetas and etas would actually be a bunch of constants. We had two conditions. We had shown that both of these conditions were basically the same. And from these conditions, since they are valid for all values of alpha, we use alpha equal to 0. And we found out that Cjkl, these constants are basically eta jk comma L at 0 minus eta jlk at 0. And using this, and using the fact that we have the Taylor expansions, and if we have the form of the Taylor expansion of the fj's, whose derivatives are beta j's, we showed that they are actually related to the Taylor expansion coefficients AJKL in this particular manner. CJKL is basically the anti-symmetrized version of AJKL. And this is something which we did not write down before, but it's sort of the same thing. This equation is essentially equivalent to this equation. At this quantity, delta LMN is equal to 0. We are going to use this equation to reconstruct the group from the structure constants later. So this is going to be useful there. Delta LMN is basically this equation where the etas, the two etas have been taken to the other side by using the inverses as i's. And you have, of course, brought the minus CJKL times xi term to the other side. And you are calling this whole thing delta LMN, which is a function of alpha which identically vanishes. Okay, any questions about this? Or is everything clear? If you have not understood any particular point here, you can, of course, ask. If not, and of course, keep on responding from time to time because I would have to be sure that I'm actually connected. Somebody was trying to join, or I saw a message a while ago. No, but if it's somebody from either Kolkata, you should be able to join anyway, right? So I don't have to do anything. Okay. So after this recap, our job essentially to try to start and do this the other way around. If somebody gave us the CJKLs, my claim is we should be actually able to reconstruct the group. That is, we should be able to find uh, essentially, at least after choosing your coordinates judiciously, you should be able to find out a function f which tells you how the parameters combine to give you the group product element. Now that's a claim, and the proof of that is actually a bit involved, and we will do it in several steps. But what we will have to do before we go there is to begin to talk about the special kind of coordinate system that we are going to use for this. These are called canonical coordinates of the first kind. Uh, I also told you before why we need to worry about coordinate systems, or why should the choice of coordinate systems be useful? Because this task of reconstructing f from C is obviously doomed from the very beginning if you are looking for a particular f. Why? Because if you change your you can always change your coordinates in such a way that f changes away from the origin. But near the origin, f stays essentially the same. Now, if that is the case, then these quantities, which essentially talk about how f behaves close to the origin, will not change. So CJKs will not change. But the fj's or even the eta j's, which are derivatives of f at zero, of course. The first argument is zero, so that's at the origin. The second argument is alpha, which is that is when you look at the derivative here. Here you are actually differentiating fj beta alpha with respect to beta. Beta is zero, but alpha is not zero. Alpha is anything. So this is actually not just the behavior of fj close to the origin. Here, fj far away from the origin also comes into account. So by changing the coordinate systems in such a way that fj's change far away from the origin, I can actually change the eta jk's while keeping the cjk's intact. So the possibility of a unique eta jk and hence a unique fj by integrating that coming out of cjk's is doomed from the very beginning. Because you have a choice of coordinates, you should be able to get infinitely many fjs starting from cjk's. However, our job is not to find out a unique f. We know there cannot be a unique f. But our job is to actually find a coordinate system for which this job is easy to do. And in that particular coordinate system, find out what the product law is. Of course, the product law is a law between elements of the group. So if you find it out in any one coordinate system, that will essentially tell you what the group is. So first, we'll talk about this particular coordinate system. And in order to go there, we will have to talk about a particular kind of subsets of which every Lie group has. They are called one parameter subgroups, not just subsets, subgroups. So our topic today, the first topic, are these one parameter subgroups. These are abelian subgroups which every Lie group has. Now the Lie group itself, of course, may not be abelian, but we are looking at a particular kind of abelian subgroup of these of a given Lie group. So that in itself should not come as a surprise, even for a discrete group. Let me just give you the analogy here. For a discrete group G, suppose an element A belongs to G, then A square, A cube, this sequence, we had argued Okay, this I don't know whether I have given you the argument in the class, but it's a pretty simple argument to show that this has to stop somewhere. Some At some value s, the s has to come back to identity. And therefore, what you have is a bunch of elements a squared, a cube up to a to the power s, which is the same as identity. So s distinct elements, which actually form a subgroup of the group G, in that is called a cyclic group generated by A. So every group actually has abelian subgroups. And here, what you see is if you take e to the power m and multiply it by a to the n, which are both elements of the group. Of course, m and n here are actually integers, but integers modulo s. This will be a to the power m plus n mod s, right? Because if m plus n becomes equal to s, this is basically the same as a to the power 0, which is effectively the same as e. And then it keeps on repeating over and over again. Now, very similarly, in the Lie group, we can find a family of elements. I'm calling them A, but now to distinguish this from a particular element A of the group that we have been using before as a notation, I'm calling this A of sigma, where sigma is a real number. So the difference between the discrete cases, basically, the other elements were a to the m, where m ran from 1, 2, 3 up to s. Here we have A of sigma, where sigma is some real number, not just an integer. But we are looking for a subgroup like this, where elements are parameterized by some real number sigma, and we have this property a sigma times a tau, product of two such elements within this subgroup is actually a of sigma plus tau, which of course means is the same as a tau a sigma. So if you have a bunch of such elements, and in fact the existence of a bunch of such elements is sort of obvious given the analogy with this, and we will actually construct such elements anyway later on. Then you have what is called an one parameter subgroup, and immediate consequence of this definition is A of 0 should be what?
The
Or
identity.
should A of, yeah, because if you put in A of 0 here, that's the same as A of 0 plus tau, so it's the same as A of tau, and that means A of 0 has to be the identity. And what about the inverse of A of sigma? After all, to be an look, the reason why I have to show this A0 equal to identity is really because I want to prove that this is a subgroup, right? A subgroup means the identity has to be in there. The inverse of every element has to be in there. Because the product of two such elements is one such element. That's there in the very definition. So rather than that,
A of minus sigma.
this has to be A of minus sigma. Again, something which is clear from this definition. So as sigma runs over an interval of real numbers, all we have to do is ensure that this interval is either the entire real number set, or it's a set which, if it has sigma, it also has minus sigma. And it, of course, has to have 0. Typically, it's some either the real number set itself or some interval from minus, say, n to plus n, with all values in between. And this is what you're going to get as a composition rule there. Now, each of these A sigmas, of course, will have parameters. Remember, our group has a coordinate system, so every group element has parameters. So A sigma will have parameters. Again, the parameters of A we have called alpha 1, alpha 2, up to alpha r. And each of these parameters, of course, will depend on sigma. So this is very much like the alphas that we talked about before, but now these alphas are not fixed numbers talking about a particular group element. These alphas are functions of this parameter sigma. Okay? Clear? So our question is, can we say anything about the functions alpha j sigma for which you will have this property? Okay, how do the parameters for elements of the one parameter subgroup depend on this parameter sigma, which is a single parameter which rules the entire subgroup? Remember the, okay, so now just because I'm using the word parameters too much, let me change nomenclature a bit. I'm going to call alpha j is coordinates for the group element, and sigma is the parameter which parameterizes each one of the coordinates. So as sigma changes over the real number line, the coordinates of the group element changes, which of course is in one-to-one correspondence with the group elements. So the group elements themselves also change. The question is, how do this, how does this equation, the defining equation for one parameter subgroup, translate in terms of the parameter of the coordinates alpha j? How do I rewrite this equation? Simple. Alpha j for sigma plus tau. When you give sigma plus tau as a parameter and you get the coordinates alpha j for this new element, these are of course coordinates for a sigma plus tau. That is the coordinates for a sigma times a tau and a tau times a sigma. So what should this be? A tau of
Fj
course
of
has fg of,
alpha j tau alpha j sigma.
well, don't say alpha j.
Oh,
Fj, then will seem like fj only depends on alpha j. That's not really true. Fj depends on all the alphas, right? When you say f of alpha comma beta, these are functions of all the 2R parameters that you have. R for A, there is alpha 1, alpha 2, alpha R, and R for B. So this is really this. You wrote fg of alpha j sigma alpha j tau, it would seem to imply that alpha 1 only depends on alpha 1 of sigma and alpha 1 of tau. That's not really true, right? Clear? Of course, this also has to obey another equation, which is this. These two must be the same because we are in an abelian subgroup. These two things are of course not the same in general. Fj doesn't usually say the same if you interchange alpha and beta, unless of course you're dealing with an abelian group. Here the group itself may not be abelian, but the subgroup you're looking at is definitely abelian. So this will work. Now, what we want to do is to write down a differential equation which alpha j sigma obeys, and from that, of course, write down. I try to solve, in principle, try to solve for these alpha j sigma. At least have a framework by which, given these functions f which describe our group, we should be able to find out the particular form of the functions alpha j of sigma such that we get a one parameter subgroup. But in order to write a differential equation, the obvious thing to do would be to change the argument by a small amount and see what happens. Say alpha j sigma plus, let's say tau is replaced by delta sigma, a very tiny infinitesimal quantity. So this according to the final equation that I wrote down is fj of alpha delta sigma, alpha sigma. Now remember, these alphas should be smooth functions of sigma because our original a sigmas are smooth and alphas are smoothly related to the group elements. Therefore, what can you say about the size of alpha delta sigma? Remember, when if delta sigma is your delta sigma, you are putting 0, you should get alpha of 0, which is of course 0, right? So when you put in alpha of delta sigma, what do you expect?
should be close to the identity.
Should be close to the
Zero. Close to zero. Sorry.
should be close to zeros, a bunch of zeros,
Oh, sorry.
right? So let's say, so this is a very small bunch of parameters. Now, of course, if you have a function where you have a bunch of very small parameters put in, the obvious thing to do would be to look at the Taylor series, which is replace the first thing by 0 and alpha sigma. That's, of course, the zeroth order term. Plus, what will happen? You will take the derivative, which is the first k parameters. These are in the first k parameters, beta k or beta alpha, and put beta equal to 0. And then multiply this rate of change by alpha k for delta sigma. Is that okay? And of course, higher order terms. This is the Taylor series, nothing else. Is that clear? All you are saying is if J has here are arguments behind which are all okay, this is beta alpha sigma. The beta here is just placeholder, it's just telling you that you have the first bunch of parameters, first R bunch of parameters, each of which are actually tiny in the actual case where you're using it. So what you do is find out the rate at which fj changes with beta and multiply by the change of the beta. Change of the beta is from 0, it has changed to alpha k delta sigma. And then of course sum up over all k, which is implied. So how much is this? Fg of 0 comma alpha sigma, how much is that?
Alpha j of sigma.
Good. And what about this quantity? What is this? Derivative of the functions representing the group product with respect to the first bunch of arguments. Yes, what are these?
Eta jk alpha
These
sigma.
are nothing but eta jk's at alpha sigma. Now we need to rewrite this a bit. Alpha k delta sigma, that is of course nothing but, okay, let me just write this first on the side. Alpha k when you change sigma very little from 0. Basically alpha k at 0 plus d alpha k d sigma. This is a single parameter. Remember, this is a function of a single variable. So this is ordinary Taylor series in one variable. Right? This, of course, is sigma equal to 0. So what is alpha k 0? That's 0. D alpha k d sigma at sigma equal to 0. That tells us that if you think about these alpha k sigmas, okay. First of all, how can you think of these alpha k sigmas as sigma changes? Note that alpha 1, alpha 2, alpha 3, alpha r. These are coordinates for a group element, but these are also a bunch of r real numbers. As you change sigma, what is happening in the r dimensional real number space, capital RR? As you change sigma, the points on the group move, right? They move away from the origin because they were at the origin at sigma equal to 0, and they can move away from the origin and move over the group. But when you're looking at the coordinates, they of course move on small r dimensional real space, right? So if you have a bunch of small r number of coordinates changing with sigma, and you have to plot them in this capital R to the R space. Okay, unfortunately, too many R's. Capital R here is the boldface R for the real line to the small r, the order of the Lie group. What do you get? What kind of a thing do you get? Suppose you had three coordinates x, y, z. They were changing with the parameter tau. And you plotted x, y, z with tau. What would you get? You plotted the point x tau, y tau, z tau, and let tau change. Think of real world. The particles coordinates x, y, z, and you get a curve. You get the trajectory of the point in physics. Here you get a curve, right? A curve in this r-dimensional space. And d alpha k d sigma at sigma equal to 0. What is the significance of this quantity?
Slope of the curve.
Well, it is actually, if you take all of them together, that is d alpha 1 d sigma, d alpha 2 d sigma, d alpha 3 d sigma, and so on, at sigma equal to 0, put them together, what you get is, well, not really the slope of the curve, because it's not a single variable curve that we're talking about. This is really a, but it's something very close. It's a tangent vector to the
A plane.
curve at sigma equals 0.
Wait,
Sorry?
nothing.
No, these numbers, d alpha 1 d sigma, d alpha 2 d sigma, up to d alpha r d sigma, these are numbers. They're numbers because you're evaluating these derivatives at sigma equal to 0. So these bunch of r numbers, which we are going to call t1, t2, tr. Well, we are going to call them t1, t2, tr for an obvious reason. They are nothing but tangent components, right? These together make up the tangent to the curve, and these are nothing but the components of the tangent at the origin, right? Clear?
Thank you.
Okay, so this is simply tk delta sigma plus order delta sigma squared, right? This is 0, and these are tk is just a name that I've given. These are just tangent components at the origin. So this thing, okay, sorry, I didn't finish this thing. I already wrote down this as eta jk alpha sigma. The alpha k delta sigma, which we took a break to figure out, is nothing but tk delta sigma. So we get here into tk delta sigma plus higher order terms. So this is alpha j sigma plus delta sigma is equal to this. So the immediate conclusion from this is about the derivative d alpha j d sigma at any sigma. What does it work out to be? What is the derivative? You change the sigma to sigma plus delta sigma, subtract the original value of alpha j sigma from it, and then divide by delta sigma, and take the limit as delta sigma goes to 0, right? That's what the derivative is.
Eta jk tk.
It's going to be eta jk at alpha sigma tk. Of course, the higher order term will not show up. This is an exact statement. This, if you stopped here, that would be an approximate statement. You're ignoring delta sigma square order terms. However, when you're talking about the derivative, you are taking the limit as delta sigma goes to 0 after dividing by delta sigma. The higher order terms will have delta sigma left in them, so they will not be there. So what do we have here? We have a bunch of differential equations for the functions alpha 1 sigma, alpha 2 sigma up to alpha r sigma. If you have told me for the functions fr, if you have given me fj, from that I know what the eta jk functions are. So what do we have? We have a bunch of differential equations on the right hand side of which you have eta jk of alpha 1, alpha 2, alpha r of sigma into tk, of course. So basically, these are a bunch of coupled ordinary differential equations. Let me emphasize the difference between this and this set that we had. This one. These were a bunch of coupled differential equations, right? But these were a bunch of coupled partial differential equations. These are actually a bunch of coupled ordinary differential equations. These ones. The ones which will give me alpha 1 sigma, alpha 2 sigma for a OPS, for a one parameter subgroup. Okay. Of course, we need initial conditions. We need to, but that's already there. Alpha j 0 is 0. We already know that. Right? So, in principle, we have done our job. If you have given me the group, that means you have given me the function f, and hence eta jk, which are nothing but derivatives of the function f. I can, in principle, solve this bunch of coupled ordered differential equations, starting with this initial condition alpha j0 is 0, and find out alpha j sigma. So, in principle, our job of finding a one parameter subgroup is done. But do we still have to check something after doing this? That is, first of all, solving this may be very difficult. Eta j may be horribly complicated functions. And so this will be a bunch of nonlinear differential equations which may be difficult to solve. But let's say I grant you that. These are difficult to solve. But in principle, we can solve them. And frankly, we will see that we will solve them only in the simplest possible situations. And the fact that we can solve them is enough for us. We don't really need to solve them explicitly unless somebody forced us to do it in an assignment or an exam. In most cases. Very rarely do we really have to explicitly solve the equations. But the fact that these equations can be solved is important. But what did we do here? We started with the assumption, not the assumption, but the definition of a one-parameter subgroup that alpha j sigma plus tau has to satisfy this. And then we said that, okay, if I took for tau a very small quantity, from that we landed up with this differential equation. Bunch of coupled differential equations with the initial condition alpha j0 equals 0. And in principle, we can solve them. The question is, if I manage to solve them, will the resulting alpha j sigmas give me a one parameter subgroup? You understand the import of the question? If we had a one parameter subgroup, we know that this differential equation has to follow from that. That's what we proved right now. The question is, if I have a solution to this bunch of equations, does it necessarily give me this or this? Do you see why this is an important question to ask? Because sometimes, especially physics, as physics students, we often don't worry about this part of the thing. If I have a condition which I have need to obey, from that I've derived something, I usually assume that if I can handle the derived thing, then the original condition is automatically satisfied. But that's not necessarily true. All we have shown is, if this is true, if you have a one parameter subgroup, you are going to get this. Right? What we have not shown yet is that if you solve this, whatever you get will also satisfy this equation. That one thing does not obviously follow from the other may not be a very obvious thing, but we have already seen this before, right? We have already proven before that this condition, this bunch of differential equations, any solution to this, which we obtained this from the associativity condition. But then we went on to show that if you manage to solve this, the resulting functions will satisfy the associativity condition. Right? So that's still something that you need to show. Okay? So equation and the claim is any solution to this equation will satisfy fj of alpha sigma. And the way we prove this is the way we proved the associativity condition. The same way we say that, okay, let's call the right hand side of this equation Rj, that is R1, R2, R3, there are small r such. And then right hand side, let's call them L, sorry, Of course, I wrote it wrong. This should be Lj equals Rj, right? Because L and R were being used for left hand and right hand side of the equation. So how do we show that Lj has to be equal to Rj? We will show that Lj and Rj will obey the same differential equation, the same initial condition, and hence they must be equal. So how do you show that? Straightforward. Let's call this Lj of sigma. Okay, just suppress tau as a parameter. Tau is always hanging out there, but let's treat these as functions of sigma. And then what does this tell you about dLj d sigma? Lj is this quantity, alpha j sigma plus tau. Can you tell me what that is going to be? Yes? What do you get when you differentiate this? Remember, you already know what you get when you differentiate d alpha j d sigma at sigma. You get this. What do you get when you differentiate alpha j sigma plus tau?
You get eta jk alpha sigma plus tau times tk, I think.
So you get eta jk. Alpha sigma plus tau is nothing but L. So let's write that as L into tk. You would have to multiply that by the derivative of sigma plus tau with the sigma, which is of course 1. So here's what you get. And what's Lj at sigma equal to 0? That's nothing but alpha j tau. So that's straightforward. This is what Lj obeys. What about Rj? What equation does Rj obey? There's a bit non-trivial because basically you have to actually differentiate with a sigma, but if this right hand side is a function of sigma only through the fact that alpha is a function of sigma and alpha of sigma is an argument of Sj. So basically chain rule. At alpha tau, where beta is alpha sigma times the derivative of beta L, which is of course alpha L sigma, right? That's all there is to it. So what is this quantity? Well, this is just chain rule, right? And now I have to apply the chain rule. What is this quantity going to be? We already know a formula for this. Derivative of the function f at any value of beta. That's going to be eta j. Okay, let's call that m. At fg of beta, fg of alpha L comma alpha tau, but that's nothing but r. So eta j m at r. Xi m L at beta, which is of course alpha sigma. Right, this is nothing but our formula that we got from associativity. And now I put in d alpha L d sigma, which by our equation that I wrote down just a while ago is nothing but eta L, let's call that n alpha sigma Tn. Now what is this? Right? Because xi and eta are inverses. And of course, xi and eta for the same argument are inverses, and you have alpha sigma for both of them. And therefore, this is eta jm r tf drj basic, which is exactly the same differential equation as for Lj, right? dLj d sigma is eta jk L tk. Here it is eta j, of course, I wrote this as m, but I could have written this as k just as well. Eta j m r t m. And what about rj0? Of course, when you put sigma equals 0, alpha sigma becomes 0, so fj0 alpha tau is nothing but alpha j tau. Same initial condition as Lj. So Lj and Rj obey the same initial condition. So what we have done, same differential equation, same initial condition. So they are essentially the same. Okay, which means that if your functions alpha j sigma are solutions of this, then this equation, the one parameter subgroup equation is satisfied, and you definitely have found the genuine one parameter subgroup. Any questions so far? Okay, none. What I'm going to do is now we are going to move on to, well, I said we will not solve the equation, but we will actually figure out some things about the equation which is enough for us to introduce the notion of canonical coordinates of the second type. Firstly, let's look at this. The equation that we wrote down, sorry, of alpha tk. And of course, we have this initial condition. Now, notice one thing. What we have here are solutions to this equation, which will depend, of course, on sigma, but what else will they depend upon? If you have a given group, there is fj, eta jk, these are given quantities. So the solution to this equation, what will they depend upon? Will it depend only on sigma or something else as well? If you are given the group, the function fj's are given, so eta jk are given functions. So you shouldn't say they depend on the function f or the function eta jk. They are sort of given the moment the group is given. But are there any other parameters here which alpha j can depend upon? Although we are calling it alpha j sigma, there are a bunch of parameters here which we have not written down when you wrote alpha j sigma. At least parameters which parameterize solutions to this equation. What are they? Yes? Should be
Is it the
obvious.
chart?
No, look, charts, everything, these are given quantities, right? So we are not saying, of course, you change your chart, these things will change, the f will change, the eta will change, and so on. We're not asking about that. I've fixed the chart, I've given you f, I've given you eta, everything is given. So these solutions, will they depend only on sigma or will they depend on something else, some other numbers which are actually right there, staring right there in the face? They're right there in the equation.
Derivatives at 0.
Derivatives of what at 0? Alpha j is at 0, right? That's what you mean, don't you? Derivatives of what at 0?
Derivatives of alpha j's. I mean, tk's are the initial
Right. Not initial condition so much, but basically what you have is the initial tangent at the origin
Yes.
that actually depends on what numbers you are going to get, right? If you target a different bunch of initial derivatives, that is a different tangent vector, you will go somewhere else. Clear? Right?
Yes. Yes.
So, these actually depend not only on sigma, they also depend on t. T meaning the abstract, you could say t is the abstract tangent vector to the group at the origin, or you could just say T is that object whose representation essentially is through these numbers T1, T2 up to TR, which are nothing but components of tangent in the R dimensional space of the curve. There is a tangent at the origin. So this is the zero, the origin of RR, and these curves all go through the origin. And at that point, you have the tangent, which is given by T1, T2, TR. And that tangent essentially is what is hidden here. Alpha j, we said alpha j depends on sigma, but of course alpha j depends on T as well. So what we have are R functions of how many parameters each, how many arguments each, how many arguments are here for
R
each of the
plus
R
one.
functions. R plus 1, right? Because 1 is the sigma. You guys talking about one parameter subgroup, right? So one parameter subgroup, fine, you have got one of the sigma is one of them. But the important thing is the R parameters T, the T1, T2, TR actually determine what the alpha J's are going to be. So they have R plus 1 arguments here. Now, having said that,
Sir?
you can also see one thing. Yeah, go ahead.
Sir, but if we don't know the, so our solution here will depend on the choice of TKs which we take, right? So how can we say that that is
Exactly.
not an initial condition, which we are
It is
assuming?
it is an initial, it is in a sense. So point is, do you get one OPS? The answer is no. You get infinitely many OPSs, one for each of these T choices.
Okay. So this is not
Change your T
unique
choice,
then.
you get another. No, nobody says that there is only one parameter subgroup for a given group. All we are doing is saying is we want to find a one parameter subgroup. A given one parameter subgroup is actually parameterized by whatever initial T's you choose. If you choose the T's, you're going to get one bunch of elements. One bunch of, so remember each point on this curve, each of the infinitely many points on this curve, as you keep on changing sigma, they actually give you coordinates for a point on the group. So each of these give you a bunch of group elements. And each of these group elements, of course, satisfy alpha sigma into alpha tau is alpha sigma plus tau. Okay? Or
So, so
A sigma, the group element is,
each parameter space
so,
is parameterized by TKs, not sigma. Then,
no, the point is, let me just put it this way. Each curve here is parameterized by the TKs. But once you fix the TKs, you get a curve where the only parameter is sigma. Because once you have T is fixed, now the only thing that changes is sigma along this. Right? So you
yeah.
get
So
A
so two
sigma.
different curves will correspond to two different one parameter
So
subgroups.
so you will get maybe A tilde sigma, A tilde tau on this. You should actually use a different notation because or rather, instead of saying this is A sigma and this is A tau, what you say is, and this is A tilde sigma, A tilde tau, and then use for another tangent vector, the third tangent vector, you get A double tilde sigma, double tilde tau. That becomes very, very cumbersome, right? So that just says that these actually are points which depend not only on sigma, they also depend on T. So basically, the T tells you which OPS you're talking about, and sigma tells you where you are on that OPS.
Yes, sir. So A tilde sigma,
Yes,
A tilde tau are different, is a different one parameter space from A sigma.
subgroup, yeah, exactly. It's a different one parameter subgroup from the one which is where A sigma and tau inhabit,
Okay.
but they also form
Okay.
a one parameter subgroup.
Okay. Okay.
So
Yes, sir.
the one
Got it.
parameter subgroup is characterized by the tangent of the identity, and A tilde sigma, A tilde tau will be one set, A double tilde sigma, A double tilde tau will be another subgroup, and so on. There will be infinitely many one parameter subgroups, in that one for each initial condition. Although there's one thing which is slightly, suppose I took, instead of this T, I took another T which is only half as long. Let's say. Instead of the TKs, I took TKs which were half. will you really get a different one parameter subgroup? Instead of this T, if you take a different tangent, you get an entirely different curve. But instead of this group tangent, if you take something which is half as long, that is all the TKs were halved on this side, right? Let's say. But from this equation, it should be obvious that if you use, instead of sigma, if you use 2 sigma, you'll get the same value for alpha j's, right? Is that clear? T, if T were half as big, as sigma change, you will trace out the same curve, but only half as at half speed, so to speak. Which means every point will be visited. The same subgroup will be obtained. Subgroup, after all, is a subset of the group. The same elements will come, but at different, at twice as big a value of sigma. Is that okay? In general, if you were to notice that if you were to multiply by lambda on both sides, where lambda is some number between, let's say, some positive number, let's say. Doesn't even have to be positive, even negatives would do. Anyway, what does it tell you? That if you start with lambda tk, and instead of sigma, use sigma by lambda, you would essentially get the same alphas, right? Is that clear?
Yes.
Which essentially means that although we have been saying that alpha j's are functions of sigma and t, that is r plus 1 arguments, that's really not true, because would be exactly the same, right? If you choose a t which is lambda times bigger, you would just get to the same point only at a sigma which is 1 by lambda times. That is, you choose a t which is half as big, you get there at 2 sigma. You choose a t which is twice as big, you will get there at half sigma. Now this means, now I'm pretty sure you've seen such things several times wherever you have scaling arguments like this. And you can actually use a scaling argument, like say, where else have you seen scaling arguments? By the way, where a function of multiple variables actually depend, where invariant or change in a very special way. When you scale the arguments, where else in physics have you seen them? Now, I'm pretty sure everybody has seen them at least in one place, which is in thermodynamics. Haven't you? If you scale all the extensive variables parameterizing a state, you're essentially talking of lambda copies of that thing. All the extensive state variables change by a factor lambda, all the intensive ones don't change. That's the standard set. So this alpha is sort of like those intensive variables there. Or you have seen them, I'm pretty sure you've also seen them in a more advanced context, in the context of scaling phenomena and critical phase transitions. I hope everybody has seen that. This should not be an advanced condensed matter thing. This should be there in basic condensed matter. Haven't you seen that? Physical quantities which scale in a particular manner which in your arguments. At least thermodynamics. Something like
Yes.
if you have U,
Yes.
which is the function of SVM, and you change S by a factor lambda, this by a factor of lambda, this by a factor of lambda. That's lambda times U SVM.
Yes. Yes. Yes.
Now, here, one important thing about scaling functions with scale is that you can actually reduce the number of arguments. Why? You can choose, say, lambda to a special value. A special value, for example, you can choose lambda to be exactly equal to sigma. To do that, you see that this thing becomes alpha j of 1 and sigma t, right? Which is of course correct, but it also tells you that ultimately it only depends on sigma t. It does not depend on 1. 1 after all is a constant. It does not depend on sigma or t separately. It only depends on sigma t. That is a function which I should use a different name for. Chi j of sigma t. Is that okay? Right?
Yes.
Okay, by the way, what is the corresponding thing as far as thermodynamics is concerned? What would you get here if you use the same kind of argument? Was a typical choice which is often made for lambda, which makes one of these arguments essentially go away.
1 by V, I think, right?
Well, 1 by capital N more likely. 1 by V would also work, but if you use 1 by capital N, as per number of
Ah.
moles,
Hmm.
you will get basically lambda. This is basically what happens is U for SV, small v, that is capital S by N, capital V by N, is capital U of SVN times 1 by N, or you essentially say U is N times small u of small s and small v. So if you take the molar energy, multiply that by the number of moles, molar energy, what is very important, which is often missed, is multiply the energy per mole by the number of moles, you get the total energy. That's a trivial statement. But the non-trivial thing here is the molar energy depends only on the molar entropy and the molar volume, not on the actual number of moles, not on the entropy and the volume, but only on the molar entropy and molar volume. That, by the way, is actually quite a non-trivial and also quite important result. That may not seem like much, but many of the properties of thermodynamics are sort of dictated by this kind of behavior. Okay, that's moving too far away from our topic here. But basically what we have is a bunch of functions. The alpha j's are essentially described by chi1, chi2, chi r functions of r arguments each. Right? The sigma t, how many numbers are there? Sigma t1, sigma t2, sigma tr. There are actually r numbers. Right? Okay. Now, what can you say about chi j's, these functions? If you put in 0 as an argument, what will you get? Well, chi j at 0 is the same as alpha j 0 comma t, right? If you put x, that is sigma equals 0. That is, if you put no matter which t you start from, you're putting sigma equal to 0, and therefore you get chi j at 0. 0 here, of course, is not a single number 0, it's a bunch of r numbers, each of which are 0. And here, this 0 is, of course, one single number, the parameter is sigma. What was that? That's 0, right? So chi j 0 is 0, that's trivial. What about chi j t for small t? Well, again, that's easy. What should it be? You just treat this as alpha j sigma t for small value of sigma and large value of t, and then just use this. This is just, or rather, let's put in sigma here explicitly, that will be easier to see. chi j sigma t, let's say sigma or t, either of them are small, so that sigma, sorry, it's not sigma comma t, it's sigma times t, plus of course alpha j sigma comma t. And we know what it is when sigma is small. What is it? If sigma is 0, what is it? 0. When sigma is small, what is it? Come on. If you know a function at 0, you want its value at a small value for the variable. What do you do? We have been doing that all the time. Essentially Taylor series, but basically you do d alpha j d sigma at sigma equal to 0. Right? And what is d alpha j d sigma? And into sigma. So this is approximately sigma times d alpha j d sigma at sigma equal to 0. But what is that?
Tj.
Of course, plus higher order term, that is order sigma square. Okay. So chi j, when you give it t as an argument, a small t, it's like tj. Right? I'm just calling sigma t here, the actual argument given. Plus, of course, order t square terms. T square meaning t1 square t2 square order terms. So this actually also tells you what delta jk is, sorry, partial derivatives. What is this? From this, it should be obvious.
Delta jk.
Okay, what does it tell you about the matrix that you make out of del chi j del tk?
At t is equal to 0 will be identity.
Yeah, at t equals 0 will be identity, but we are, again, an argument we have used before. The identity means is invertible, right? So at t equals 0 it's invertible, but when you move away from the origin, use a finite t, not t equals 0. Will it still be invertible? The answer is there will at least be some region around the origin where it will be invertible. Okay. Again, all I'm using is smoothness. If a matrix is invertible at a particular point, it has to stay invertible in a region around that point. A non-zero value cannot jump to 0 immediately. It has to, there's a region where it's still not there. In other words, the determinant of the matrix cannot change from 1 to 0 immediately. It has to go through a distance. So in between, you will have an invertible del chi j del t. Now this gives us something very important. It tells us, and this is going to be the central theme of what we have actually, is that there will be a region around the neighborhood where if you are given me an A with coordinates alpha j, I should be able to find the t by solving this equation. Remember, solving this equation, I should be able to solve the differential equation which I get for chi j, which is essentially the differential equation from alphas. And we should be able to find out some chi j, some t, such that chi j t is exactly equal to alpha j. In other words, given a point in the neighborhood of the identity, we should be able to find some tangent. So, of course, a point in the neighborhood of the identity has some coordinates, some bunch of coordinates. The idea is I should be able to find a curve which goes, one of these one parameter subgroup curves which goes through that point. In other words, I should be able to find a tangent vector which ensures that, okay, this might go to the curve at say some value of sigma. Let's say sigma equals 3. But then I can all I can do is I will make the tangent vector that I started with 3 times smaller. Ensure that this graph curve will go through this point at sigma equal to 1. Okay, so in other words, chi j t. Remember, chi j sigma t is the parameter. Will be equal. But if sigma equals 1, then chi j t is going to be alpha j. For every point in the neighborhood of the origin, I should be, or neighborhood, every group element in the neighborhood of the identity, the corresponding parameters of points on the origin, I should be able to find some tangent which goes through this point. So which gives a curve which goes to the point, and then I can rescale the tangent if needed to ensure that it goes to the point at t equal to 1. And that gives me a unique tangent. Why is that important? It's important because for every group element in this neighborhood, I now have a unique tangent vector, which means that instead of using our original coordinates, the alpha 1, alpha 2, alpha r, we can also use that particular T1, T2, Tr to parameterize this point. Is that thing clear, or is it becoming too difficult to understand? Note that for every point here, I should be able to find a curve which goes through the point, and I should be able to scale my tangent so that it goes through that point exactly at sigma equal to 1. Once you do that, I've got a unique tangent for every point. So give me the tangent, I will give you the point. Give me the point, I will give you the tangent. Whenever the tangent is as good a parameter, or the tangent is as good a coordinate as the original coordinates. Because what are coordinates? There are a bunch of numbers which, if you are given them, you can find the point uniquely, and vice versa. The same goes for this. So give me a tangent, I will find you a point uniquely. Give me the point, I will find a unique tangent for you. So this gives us a new choice of coordinates, the so-called canonical coordinates of the first kind. We are going to explore the properties of these and talk about how they're going to help us to find out solutions to this original problem, given the factor constants, how do you reconcile the group, in the next class, which of course will be at 5 on Wednesday. So any further questions on this? Okay, I will explain this in a bit more detail in the next class, because I think this is a very important point that we will have to bear in mind. Okay, if there are no further questions, then okay, then let's stop this class for today. We are going to meet again on Wednesday at 5. Okay, 5, maybe 5 minutes past 5.